In this video, we're going to go over some practice problems from chapter 8 of our textbook. Starting with section 8.2 here, we're going to be working with the quadratic formula. So for these two questions here, we want to use the quadratic formula to solve each of these equations. So first thing that I'm going to do is write out the quadratic formula here. We're going to end up with two solutions for our x value. The formula is given by opposite of b plus or minus the square root of our b value squared minus 4 times a times c. This is all under our square root. And then we're dividing this entire thing by 2 times a. So what we want to do is figure out what our a, b, and c values are from this equation and plug them directly into this formula. Now, right off the bat, you might be able to tell what our a, b, and c values are. But before we do anything, we want to make sure that this is written in standard form. So we bring the appropriate signs with us for each of these coefficients. So in standard form, we know that we're going to have all of our terms on one side of the equation and 0 on the right-hand side. So in order to do that, I'm going to subtract 6x from both sides of the equation and add 1 to both sides of the equation. Doing so, we're going to end up with 9x squared minus 6x plus 1 is equal to 0. Now that this equation is in standard form, we can easily see what our a, b, and c values are going to be. A is going to be positive 9, B is going to be negative 6, and C is going to be positive 1. Now, going back to this original equation here, we might have been able to tell what these values were, but if we write it in standard form here, it's much easier to make sure that we take the appropriate sign with us. So with that, we're going to go ahead and plug these values into our quadratic formula. So again, we're going to get two solutions. We're going to end up with x is equal to opposite of b. Well, b is negative here, so the opposite of that would end up being a positive. Then plus or minus the square root of our b value squared minus 4 times a times c. We're taking the square root of this whole thing, and then we're dividing this entire thing by 2 times our a value. All right, so from here, let's keep simplifying. Underneath, this is a positive 6, underneath our square root here, we're going to end up with a positive 36 since a negative 6 squared gives us a positive value. And then we're going to have a minus 4 times 9 times 1, which gives us a positive 36 as well. So underneath our square root, we're going to end up with 36 minus that positive 36 value all over 18. So this is actually just going to be the square root of 0, and the square root of 0 just gives us 0. So we're going to end up with 6 plus or minus 0 over 18, which can be fully simplified by dividing the numerator and the denominator by 6. So we're going to end up with 1/3. So our solution set for this one is going to end up being the value that x is equal to 1/3. All right, let's do the same thing for this next equation here. Again, this is not in standard form, so the first thing that we want to do is make sure that we write it in standard form so we can take the appropriate signs with us. So I'm going to subtract 1 on both sides of this equation. I'm going to end up with 4x squared plus 4x minus 1 is equal to 0. So in this case, a and b are both going to be equal to positive 4, and c is going to be equal to negative 1. So let's plug these values into our quadratic formula. We're going to get that x is equal to opposite of our b value. So this is going to end up being negative 4 plus or minus the square root of b squared minus 4 times a times our c value. Then we're going to divide this entire thing by 2 times a. All right, so let's do what we did in the last case. Let's just keep simplifying this. Underneath our radical here, we're going to end up with 16 for our first term. Then we're going to have 16 minus a negative 16. So this is going to end up being 16 plus 16 underneath our square root. And then we're going to have 8 in our denominator. All right. We're going to end up with the square root of 32 over 8 here. Now we might want to stop here, but the square root of 32 is not going to be fully simplified. We can break 32 up into two or more factors, one of them being a perfect square. So let's go ahead and do that here. We're going to have negative 4 plus or minus. I'm going to break up 32 into 16 times 2 since 16 is a perfect square. Simplifying this, we're going to end up with negative 4 plus or minus 4 root 2 all over 8. Now, our radical term is fully simplified here. However, this would not be our final answer since this is not written in lowest terms. The numerator and the denominator both share a common factor of 4. So we'll go ahead and pull that 4 out from both. In the numerator, we're going to end up with negative 1 plus or minus root 2. And in the denominator, we're going to have 4 times 2. Taking out the 4 from the numerator and the denominator here, our final answer is going to end up being negative 1 plus or minus root 2 all over 2. So this would be our solution set. So negative 1 plus or minus the square root of 2 all over 2. And this would be our final answer. And this is how we're going to use the quadratic formula here to solve quadratic equations. Now, the last two examples in this section here, we want to tell whether the equation given below can be solved using our zero factor property or if the quadratic formula should be used instead. And we're not actually going to solve these, we just want to determine which method we should use. Now, if you haven't already done so, please check out the textbook. In this section here, in the last objective, there's a nice table that tells us how to use the discriminant. That's what we're going to be using to answer this question here. So the discriminant is going to be the value underneath our radical in our quadratic formula. So this is the discriminant value here. So we're going to use this value to answer this question here. Now, if we have a positive discriminant and it's the square of an integer, we're going to end up with two radical solutions. If we end up with 0 for the discriminant, we're going to end up with one radical solution and so on. And this is all given in the table in our textbook. But the main takeaway that we're going to use is the fact that if the discriminant is a perfect square, which also includes 0, then our equation can be solved using our zero factor property. Otherwise, we're going to be using the quadratic formula. So with that information, let's go ahead and find the discriminant of these two equations here and answer the question. So starting out with this one here, this is already written in standard form. We can easily see what our A, B, and C values are going to be. A, in this case, is going to be 4. B is negative 28, and C is positive 49. We need to know what these values are so we can plug them into our discriminant formula. Our discriminant is the value, again, underneath our radical in our quadratic equation, so that's b squared minus 4 times a times c. So we're going to plug in our values. We're going to end up with negative 28 squared minus 4 times a times c. All right, let's simplify this. We're going to end up with 784 minus 784, which is 0. Now, 0 is a perfect square. So this tells us that we're going to be using our zero factor property to solve. So 0 factor property, since 0 is also a perfect square. All right, let's look at this next one here. We're going to do the same thing, but the first thing to note here is that this is not written in standard form. So let's go ahead and do that so we can see what our A, B, and C values are. So let's add 15 to both sides of our equation. We're going to end up with 3m squared minus 10m plus 15 is equal to 0. So A is going to be 3, B is going to be negative 10, and C is going to be positive 15. All right, so let's figure out what our discriminant is going to be. All right, so we're going to end up with negative 10 squared minus 4 times A times C. This is going to give us 100 minus 4 times 3 times 15 is going to be 180. So we're going to end up with negative 80 in this case. All right, now this is not a perfect square here. This is a negative number, so that's already going to be a red flag. So this tells us that this equation is going to be solved using our quadratic formula. All right, and that's it for these two problems here. All right, so this brings us to section 8.4, where we're primarily going to be looking at applications of quadratic equations. But before we do that, let's solve each of these equations here for the specified variable. So for this first one, we want to solve this guy for d. Now, looking at this equation here, I notice that d is being squared. So this automatically tells me that if I want to completely isolate d, solve it for d, I'm probably going to end up taking the square root. Now, in order, or using the square root property. Now, in order to use the square root property, we first want to make sure that whatever is being squared is by itself on one side of the equation and everything else is on the other side of the equation. So I'm going to try to isolate d squared by itself first and then use the square root property. So I'm going to start out with multiplying both sides of this equation by d squared so that we get it out of the denominator. So I'm going to end up with d squared times I is equal to k times s. Now, like I said, we want to make sure our square term is isolated before we take the square root on both sides. So I'm going to divide both sides of this equation by I. I'm going to end up with d squared is equal to k times s divided by I. All right, so now that we have the square term completely isolated, we can go ahead and use our square root property. I take the square root on both sides of this equation. I'm going to get d completely isolated here. And on the right-hand side of my equation, I'm going to have plus or minus the square root of ks divided by I. So remember, whenever we're taking the square root or using the square root property here, we're going to end up with two solutions, and we abbreviate this with plus or minus. Now, this is not going to be my final answer, however, because using the quotient rule for radicals, this is the same thing as the square root of ks divided by the square root of I. And a radical will not be fully simplified, or a radical equation will not be fully simplified if we have a radical in the denominator. So what we need to do is rationalize the denominator, and we can do so by multiplying the numerator and the denominator here by the square root of I. Doing so, we're going to end up with, we still have this plus or minus here, and in the numerator, we're going to have the square root of ks times the square root of I. Since these guys have the same index, that square root here, we can put the entire product under one radical. So we're going to have k times s times I in the numerator. Then in the denominator here, by the same logic, we're going to end up with the square root of I times I, which is the square root of I squared, which just simplifies to I in the denominator. Now this would be our final answer because it's fully simplified. We rationalized this denominator here. All right, let's do the same thing for this next one. Now, in this case, we want to solve for L. Now, notice L is underneath a square root. So we're going to have to kind of do the opposite in this case. What we want to do is use our power rule to get rid of this square root. So we'll go ahead and do that. We're going to square both sides of this equation. To get rid of that square root, we're going to end up with p squared is equal to k times L divided by g. So now it just becomes a matter of isolating L. The first thing that we're going to do is get rid of this fraction here by multiplying both sides of this equation by g. We're going to end up with g times p squared is equal to k times L. And then lastly, to fully isolate L here, we're going to divide both sides of our equation by that k. We're going to end up with L is equal to g times p squared divided by k. All right, let's look at our next problem here. This is where we're going to start looking at applications of our quadratic equations. So we're told that a vegetable garden is in the shape of a right triangle. So as soon as I read that information, I'm just going to go ahead and draw a right triangle so we can visualize what's going on here. All right, so it says the longer leg is 3 feet longer than the shorter leg, and the hypotenuse is 3 feet longer than the longer leg. Okay, so what we're gonna do is let's let x be the length of the shorter leg here. So this is gonna be x. The longer leg, which is gonna be this side, is 3 feet longer than the shorter leg. So this longer leg here is gonna be x plus 3. And then the hypotenuse here is gonna be 3 feet longer than the longer leg. So it's gonna be 3 feet longer than this. So we're gonna end up with x plus 3, which gives me x plus 6. All right, so these are the lengths of the three sides of the triangle, and that's exactly what we want to find. Now, in order to find these actual lengths, then we need to find what x is. So in order to do that, we're going to use our Pythagorean theorem. This theorem says that a squared plus b squared is equal to c squared, where a squared is going to be one side of our right triangle, b is going to be the other side, and then c is going to be our hypotenuse for our right triangle. So with this information here, we're going to plug everything into our equation. A squared is going to end up being x squared since the length of this side is just x. The length of this side of our b is going to be x plus 3, so that entire thing is going to be squared. We're going to have x plus 3 squared. And then lastly, this is going to be equal to our hypotenuse squared. Our hypotenuse is x plus 6, so that entire thing is going to be squared. All right. We're still going to have this x squared here, but this guy, what we're going to do is FOIL it. X plus 3 squared is the same thing as x plus 3 times x plus 3. So we're going to have x plus 3 times x plus 3. So foiling this, we're going to end up with another x squared. Then we're going to have 3x plus 3x. So that's going to give us a 6x. And then 3 times 3 is going to give us a positive 9. Similarly, on the other side here, this is the same thing as x plus 6 times x plus 6. Just to be consistent, we'll go ahead and write that here as well. Then we can FOIL this. We're going to end up with another x squared and then 6x plus 6x. So we're going to have x squared plus 12x plus 6 times 6 gives us 36. All right, so from here, let's simplify, combine like terms, and see if we can solve for x. On the right-hand side here, I'm going to end up with 2x squared plus 6x plus 9, and that's as far as we can go. And then on the right-hand side here, we can't simplify this any further. We can't combine like terms. But what we can do is move all of these terms to this side of the equation and see if we can combine like terms. Since I know I'm dealing with a quadratic equation here, we only know two ways to solve these types of equations. That's either factoring or using our quadratic formula. So this tells me that no matter which method I use, I should at least write this in standard form to figure out which method to use. So let's go ahead and do that. I'm going to move all of these terms over to this side of the equation. All right, doing so, I'm going to end up with 0 on the right-hand side of my equation, and on the left-hand side, I'm going to combine like terms. I'm going to end up with just one x squared term, then I'm going to have a minus 6x term, and then a minus 27. All right, so now this is in standard form. Like I said, we're either going to factor or use the quadratic formula for this one. Now, in the last section, we talked about using the discriminant to figure out which method to use. We could totally do that. But in this case, I'm just going to try to factor and guess and check. So I need two numbers that are going to multiply to give me negative 27 and add to give me a negative 6. Well, two numbers that satisfy this would be negative 9 and positive 3. So let's go ahead and factor this and check our work. So we can check our work by foiling this. I'm going to end up with x squared plus 3x minus 9x. That'll give me x squared minus 6x. Then I have a negative 9 times a positive 3. That'll give me negative 27. So I know this is the correct factored form, and now I can use my zero factor property. It says that I must have x minus 9 is equal to 0 or x plus 3 is equal to 0. And solving for x, I'm going to get x is equal to positive 9 or x is equal to negative 3. So I have two solutions in this case, which makes sense since we have a quadratic equation. But remember, we're talking about the lengths of a garden. So in this case, x cannot be negative because we can't have a negative length. So our only option here is that x is equal to 9. So this tells us that the length of the shorter side is going to be 9, and in this case, our units are feet. The length of the longer side, which is x plus 3, is going to give us 12 feet. And then lastly, the length of the longest side, the hypotenuse in this case, is going to be 15 feet. All right, so that's how we would solve this using our quadratic equation. All right, so this brings us to our next question here. A club swimming pool is going to be 30 feet wide and 40 feet long, so given by this here. Now, the club members want an exposed border and a strip of uniform width around the pool, so given by this. Now, they have enough material for 296 square feet, and with this information, we want to determine how wide this strip can be. So, first things first, let's label our unknown value that we're trying to find. Let's let x be equal to the width of the strip. This is what we want to find. All right, now if we let x be the width of this strip here, notice that that's going to change the dimensions of the length and width of this pool, including the strip. If x is the width of this strip here, then this means this distance from here to here is going to be x, and this distance from here to here is also going to be x. So the length of this, including the pool and this border here, is going to end up being 30 plus 2 times x, since we have an x distance here and an x distance here. Similarly, if we're looking at the length of this pool here, we're going to have a distance of x from here to here, since that's the width of this strip, and a distance of x from here to here. So the length of this pool, if we include that border, is going to be 40 plus 2 times x, since again, we have two distances of x on this length. Okay, so that's going to change the dimensions a bit. But our first piece of information is actually going to be the area of just this pool here. That area is going to be the length times the width. So the area of just the pool is going to be the length times the width, which is going to be 1,200 square feet. Now, with this information, we can write an equation using the total area of the pool and the border. So let's go ahead and write this down in words here. So our total area, which is going to include this pool and this border, this strip here, is going to be the length times the width. So this is going to be 30 plus 2x times 40 plus 2x. Now this total area is also going to be the area of this pool plus the area of the border. So we're going to write this as the area of our pool plus the area of the border. Right? So this area here, this total area should be equal to everything in blue plus everything on this border. Now the total area, like we mentioned, is going to be these new dimensions here, this new length times this new width. And then we're going to take the area of our pool, which we found to be 1,200 square feet, plus the area of our border, which was given in this problem here, that would be 296 square feet. So now we have an equation and we can solve for our unknown value of x. The first thing that I'm going to do is I'm going to FOIL everything on this side here. So I'm going to have 30 times 40 plus 30 times 2x times 40, and 2x squared. So on the left-hand side of my equation, I'm going to have 1,200 plus 140x plus 4x squared. Then on the right-hand side of my equation, just adding these guys together, I'm going to end up with this. All right, so let's go ahead and combine like terms and try to write this in standard form. Again, we have a quadratic equation here, so we only know how to solve that either with the quadratic formula or by using our zero factor property. So what I'm going to do then is I'm going to subtract this guy here on both sides of my equation. Writing this in standard form here, I'm going to write my squared term first, so I'm going to end up with 4x squared plus my 140x plus my constant term of negative 296. All right, now from here, before we go ahead and factor, let's see if we can factor out any common factors. Notice that 4, 140, and 296 are both divisible by 4. So if I divide both sides of my equation by 4, I'm going to simplify this equation for us a bit. We're going to end up with x squared plus 35x minus 74 is equal to 0. Now from here, let's see if we can factor this and use our zero factor property. We're running out of space here, so I'm going to do that over here. Now I need two numbers that are going to multiply to give me negative 74 and add to give me positive 35. So these two numbers here then are going to be negative 2 and positive 37. So I'm going to have negative 2 and positive 37, and this is equal to 0. Now, using our zero factor property then, I'm going to end up with x minus 2 is equal to 0, or x plus 37 is equal to 0. Solving for x, I'm going to end up with x is equal to 2 or x is equal to negative 37. Now again, we're talking about the width, so we can't have a negative measurement. So our only solution here is going to be x is equal to 2. So this tells us the strip will be 2 feet wide. All right, so this brings us to our last example here. We're again going to be looking at an application problem. We're told that a ball is projected upward from the ground. Its distance in feet from the ground in seconds is given by this quadratic function here. So the distance is given by s of t, and it's going to depend on our value for t. It's going to depend on how many seconds have passed. What we want to do with this equation is figure out at what times will the ball be 213 feet from the ground. So we're trying to find t here, when s of t is equal to 213. So the first thing that we're going to do is plug in this value for 213 into our function. So we're going to get 213 is equal to this here. Now again, we're trying to solve for t. We're trying to find at what times will the ball be this distance from the ground. In order to do that, we're either going to use our zero factor property or the quadratic formula. Those are the only two ways we know how to solve a quadratic equation here. But in either case, we first need to write this in standard form. So I'm going to subtract 213 from both sides of my equation, and I'm going to end up with this here. Now from here, the easier method would be to try to factor this and use our zero factor property. However, if we wanted to first see if we could take out a negative 16 from this side or divide by negative 16 on both sides of our equation, we would see that we wouldn't get whole numbers here for these guys. So what we could do next is see if we can try to factor this with this negative 16 here, and we'd see that we can't. And ultimately, what we could do is first figure out what the discriminant of this would be. This would be our A, B, and C value. Plug that into our discriminant formula that we saw in section 8.2, and that would tell us whether we can use our zero factor property or the quadratic formula. Doing that, we'd see that we can't use the zero factor property, so the quadratic formula it is. What we need to do is figure out what our A, B, and C values are going to be and plug them directly into the formula. So in this case, we're solving for t. So we're going to get that t is equal to opposite of our b value plus or minus the square root of our b value squared minus 4 times a times c all over 2 times a. Like I said before, we could figure out what this discriminant is here underneath our radical, and that would tell us that we would have to use the quadratic formula. So let's plug in our known values. B is going to be 128, so opposite of that is going to give us negative 128. Underneath our radical here, we're going to have 128 squared minus 4 times a, which is negative 16, times c, negative 213. This entire thing is going to be underneath our square root, and all of this is going to be divided by 2 times a. So from here, we need to simplify this, and we're running out of room, so we'll do that over here. We're going to end up with negative 128 here still, and then underneath our radical, we're going to have 16,384, and we're going to end up with a minus here since we have, this is going to end up being a positive, and we still have this minus out front. It's going to give us a negative 13,632. And then we're dividing this entire thing by 2 times negative 16, so that'll give us a negative 32. Let's keep simplifying this here. Underneath our radical, we're going to have a positive 2,752. And then we'll go ahead and simplify this. All right. Now looking at this radical here, we actually can't split this up into two or more factors, one of them being a perfect square. So this would actually be our final answer. And what we can do is evaluate what these values actually are. So what I mean is we actually have two solutions. We have t is equal to negative 128 plus this square root and this entire thing divided by -32. If we were to actually evaluate this and plug this into our calculator, we're going to get approximately 2.4 seconds. On the other hand, our second solution is that -128 minus this radical divided by -32. Again, plugging this into our calculator here, we're going to get approximately 5.6 seconds. So what we can conclude here is that the ball will be 213 feet from the ground after approximately 2.4 seconds, and again after approximately 5.6 seconds. This makes sense because the ball is being projected upward from the ground. So the path essentially of this ball is going to look something like this. Now, if this is 213 feet from the ground, that's going to happen at two different points here. Here at about 2.4 seconds, and again here at about 5.6 seconds. So this is kind of the image of what that would look like if we were to project a ball from the ground.